Hi, my name is Peyton, and today we're going to be discussing Lab 4 circuits and capacitors. The objective of this lab was to use multimeters to measure currents and potential differences, observe the behavior of resistors and capacitors, and predict the behavior of circuits, which include resistors. An overview of the results will be both of the currents I1 and I2 were 0.02 amps, and our RC value was 6.11 seconds. There are some important concepts to understand before going into this lab. Those concepts include Ohm's law, which is change of V equals IR, energy, current, and charge conservation, the loop rule and the node rule, which heavily involve RC circuits. So the node rule involves conservation of current. Current going into the node is equal current exiting the node. And the loop rule involves conservation of energy, which is the potential difference around the closed loop is zero. In this scenario, our system is going to be the circuit and our surroundings is going to be everything else. Part 1 is the series circuit. This section included two ammeters, two 1.5-volt batteries, and two resistors. We predicted that the currents I1 and I2 would be 0.02041 amps. The actual value was 0.0199 amps, and then when reversing connection to one of the ammeters, it would just be negative 0.0199 amps. When replacing the ammeter with the voltmeter, the change in V should be 3V and the current should be 0. The change in V across the 47 ohm resistor was negative 0.8 volts and negative 1.9 volts across 100 ohm resistor. So these values are important to understand the potential difference. So this involves the loop rule and a closed circuit. So our circuit was closed in this scenario, and at the end it should have been 0 volts, but we ended up with 0.2 volts. Once again, this was done in person, so human error is inevitable, but we understand that since it is the loop rule, it should be 0. We basically found the changes in V values from A to B, B to C, all the way to G. And then we looked and we saw that the current reading was still 0.02 amps. The reading doesn't change because the voltmeter has such a high amount of resistance that no current flows through it. As you can see at the bottom, we were given a graph to start off with, and then we finished it based upon our own values that we saw. And we did that handwritten, of course. So the potential difference continued. We now have the voltmeter replaced with the ammeter in parallel with the 100 ohm resistor. The current reading went from 0.02 amps to 0.05 amps because the resistance decreased. And when the resistance is decreased, the current then increases. And then we found the potential difference based on some measurements we got in earlier parts. So the resistor for the 47 ohm resistor, we got 40 ohms. For the 100 ohm resistor, it was 95 ohms. And then R of wire and R of ammeter were both 0. And we found part A and B by doing 0.8 divided by 0.02 and then 1.9 divided by 0.02, which are values we found previously. So now we have the part 2, which is the RC circuit. The circuit involves a 1.7 ohm light bulb. We found this value ourselves. Two 1.5 volt batteries because the 9 volt one that the lab wanted us to use for the simulation was far too much to do in person. And a 1F capacitor. We saw that the light started off bright but then continued to dim as time passed until there was no light at all. The capacitor provided current to the light. It took about 15.773 seconds for the capacitor to charge, and it took about 15.348 seconds for the capacitor to discharge. Our change in V naught was 2.9 V, and then we found the change in voltage over the course of 20 seconds, and then we put it into Excel. So as you can see on the left, those are all of our data values. So you have our change in V naught is 2.9 volts. We have T, change in V, and change in V divided by change in V naught. But when we put this in Excel, we should do the natural log of the change in V divided by change in V naught. And that's going to be versus time. We're going to use the equation QC minus IR equals 0. And then the experimental RC should be negative 1 divided by the slope, which is just negative 1 divided by negative 1, or 0.1636, which was our slope, and we got our RC value to be 6.11 seconds. Now, some sources of error. We could have set up the circuit slightly wrong, making our readings not entirely accurate. We could have misread the readings on the ammeter, and some of the materials used in this lab may not have been entirely up to date, meaning that they were overused. So, for instance, that could have been the light bulbs, the batteries. Many kits also had parts missing that we all had to share. So the discussion, I'm going to be, since this was done in person, I'm answering this by asking what would have happened if it was done virtually. The first what if is just essentially asking just overall what would have been different since we're using an ideal simulated ammeter. And an ideal simulated ammeter has absolutely no resistance. This would change our measured values of current as well as our predicted values because the current would be able to move around a lot more. And then our what if number 2, which is basically just asking about the capacitor reaching full charge, like how that would have changed with the simulator since everything is ideal ideal, the capacitor should charge instantly, we need to remember that in this ideal scenario, there is no resistor present in the circuit. In our observations, we noticed that this took 15 seconds previously in person, and that's a massive difference from charging instantly. So those would be the differences between doing it in person and then doing it using an ideal simulation. Thank you so much for watching.